Here is a question on general organic chemistry. Read the question carefully and think about the answer. Let us solve it step by step. Let us now begin solving this step by step. Step 1. Identify the acidic protons in each compound. All 4 compounds can lose a proton alpha to a carbonyl, CH acidity. The key factor is how well the resulting carbanion enolate is stabilized. Compound I, 3-cyclohexanediene. The alpha carbon between the 2 ketone carbonyls is flanked by 2 carbonyl groups. This gives very strong stabilization of the enolate by double resonance delocalization. This is a 1,3-diketone, pK 5 to 7, relatively very acidic. Compound 2-delta-valorolactone, tetrahydropyran, 2-1. This is a simple lactone with only 1 carbonyl. The alpha proton next to a single ester-type carbonyl is weakly acidic. Esters stabilize enolates less effectively than ketones because the oxygen lone pairs donate back into the carbonyl, raising the pKa. pK 30+. Compound 3-tetrahydropyran, 4-1. This is a cyclic ketone with an endocyclic oxygen in the ring at position 1 and ketone at position 4. The ring oxygen is 2 carbons away from the carbonyl. The alpha protons are alpha to a single ketone carbonyl, but the inductive effect of the ring oxygen, I effect, slightly increases acidity compared to a plain ketone. However, the oxygen is not directly stabilizing the enolate through resonance. pK slightly lower than a simple ketone, 20, but much higher than 1,3-diketone. Compound 4-methyl-4-oxocyclohexane, 1-carboxylate. This compound has a ketone, C4, and a methyl ester, C1, on the same cyclohexane ring. The C to C6 protons, alpha to the ketone, and C1 proton, alpha to both the ketone and the ester if in a 1,3 relationship or at least under inductive influence, can be considered. Critically, the proton at C1 is alpha to the ester group and feels the inductive withdrawal of the ketone at C4, beta-keto-ester type relationship through the ring. A beta-keto-ester is significantly more acidic than a simple ketone, pK 11 to 13, because the enolate is stabilized by both the ester and ketone. This compound is the most acidic among the 4. Step 2. Rank by acidity. Increasing is equal to least acidic to most acidic. Compound 2. Simple lactone, single carbonyl, ester character least acidic, highest pKa, 30+. Compound 3. Cyclic ketone with ring O, single carbonyl, modest inductive effect less acidic than I or 4 but more acidic than 2. Compound I, 1,3-diketone, 2 carbonyls stabilizing enolate more acidic than 3. Compound 4, beta-keto-ester embedded in ring, both ketone and ester stabilizing most acidic. Increasing order of acidic strength to 3I4. This matches option D. Why other options fail? A. 3I4 2 places 2 as most acidic, which is wrong, lactone is least acidic. B. 2I4 3 places 3 as most acidic, which is wrong. C. I3 2 places 2 as most acidic and I as least, both incorrect. Therefore, the correct answer is D. Therefore, the correct answer is option D.